Okay, so now we're going to talk about determining empirical formulas and molecular formulas. Empirical and molecular formulas. Okay, so first of all, a definition of empirical formula is an empirical formula is the lowest ratio. If I've got a formula that looks like this, C, H, X, and Y, you know that there's X moles of carbon for every 1 mole of this compound and Y moles of hydrogen for every mole of that compound, right? Or X atoms of carbon in a formula unit and Y atoms of hydrogen in a formula unit, right? Well, empirical formulas are the lowest whole number ratios here, right? So, for example, if the formula for benzene is C6H6, the lowest whole number, this is the molecular formula because there's 6 carbon atoms in a molecule of benzene and 6 hydrogen atoms in a molecule of benzene, then the lowest whole number ratios are C1H1, which we'd simply write as CH, right? So the empirical formula for benzene is that we are much more accustomed to writing the molecular formulas. This is much more familiar to us. But we do need empirical formulas from time to time, and this is what this section is about, okay? So, in order to find empirical formulas, we're oftentimes given percent compositions. All right, so you might find, look at this, that in a 10-gram sample, you have 2.5 grams of hydrogen and 7.5 grams of hydrogen. So the percent composition, of course, right, this is a part per whole. This is straight out of the SAT. It's a part per whole, right? Can you read my writing? Part per whole. So if it's 2.5 grams of the part, in 10 grams of the whole, we divide it, and then to convert to a percent form, we multiply by 100, and we get 25%, right? And this is maybe something you might have done in your head, but it's important to, I think, appreciate the form of this, right? So 7.5 grams is the part. That's how much carbon we have in a 10-gram sample. So we divide them, multiply by 100 to use the percent symbol, and it's 75% carbon. All right, so that may be something that we need from time to time. Same thing for nitrogen. I'm going to skip this one. It's exactly the same thing, except done in AMUs now instead of... it's not actually, it's not exactly the same thing. I went too fast on that. So we may be asked, what's the percent nitrogen in ammonia? So you would take the AMUs of the mass of a nitrogen atom and the mass of an ammonia molecule, and this is a part per whole, and you divide it. So in terms, that turns out that the mass percent of nitrogen in ammonia is 83%, right? Because most of the mass of an ammonia molecule is nitrogen, okay? And the mass percent of hydrogen in ammonia is 17% or 18%, right? Okay. So now let's talk about determining empirical formulas. So what we're going to do when we're determining, we're going to follow 3 steps. Determining empirical formulas, we're going to convert masses to moles, right? Because we always have CXHY or whatever the atoms are in there. These are moles, right? Not masses. So we always have to convert masses to moles first. That's the first thing we do. And then we divide the moles of each of these moles that we calculate by the smallest number. And then we reduce. All right, so let's look at an example. So suppose that you have a compound. It's determined to contain 1.71 grams of carbon and 0.27 grams or 287 grams of hydrogen. So the first thing we do is we convert the mass to the moles, right? You've seen that in a previous conversation. You've practiced that other places. For now, let's say that is something that's accessible to you. So you've got 0.142 moles of carbon in this compound, okay, and 0.284 moles of hydrogen in this compound. So what do? Well, I think the author of this text, Flowers, likes to write it out like this, and I think this is a good way to do it, right? So he writes the moles out here. You've got 0.142 moles of carbon. Now, clearly, this is not a good molecular or empirical formula. So what are we going to do? We're going to divide each of those by the smallest of them, right? Can you see the smallest is 0.142? 0.142, and then 0.142 divided by 0.142, of course, is 1. 0.248 divided by 0.142. This is a misprint. Look at that. It's supposed to be 0.284. This is a misprint. Okay, sorry about that. It's supposed to be 0.284. 0.284 divided by 0.142 is 2. Okay, so when you divide each of those mole numbers by the smallest, oftentimes it's going to come out real nice. It won't always come out real nice. Sometimes it's going to be a little bit messy. So let's do the same thing here. We've got a compound that's got chlorine and oxygen in it. I put the more electropositive element first and the more electronegative element, right? X, Y. And I convert this grams of chlorine to this many moles. There's my moles of chlorine, and I did that by doing a formula mass, right, of chlorine. And I convert this many grams of oxygen to this many moles, right, because you got to have moles here. Now I divide both of those by the smallest number. And the smallest number is 0.15. So this goes to 1, which I leave out, right? We don't put the 1 in if it's a 1. But this goes to 3.5. That's not an integer. Wait, I can't do that. Okay. What I do then is I multiply everything by some number that's going to make that an integer. Well, you can see that that's a half, right? And so I can see if I multiply that by 2, it's going to go to a nice integer, right? So we'll do that with, you ask for help if you want more examples of that. We can certainly get more explicit, but I think most of these are going to fall to your intuition as long as you're okay converting the grams to moles. I would say that's the most common place for error here. There's a red siren going off here. That's where most people make mistakes, okay? Once you get that, if you get that correctly, then the rest of this I'm gonna suggest will fall out. Come and bring your questions to me if you don't like that. I'm gonna do another more elaborate example in just a minute. All right, so now if you're given, instead of given masses, if you're given the percents, then you should just assume that the percent composition comes from a 100-gram sample. So you convert the percents to masses just by moving the decimal point. Let me show you what I mean by that, okay? Let's come here. The bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of this percent of carbon and that percent of oxygen. So I'm going to say, well, let's start here with an element, percent, mass, formula weight, moles, okay? So the first element's carbon, and the percent is 27.29. Now I'm going to assume, I'm going to go back to the previous slide, just assume that there was 100 grams in the whole sample. And if there's 100 grams in the whole sample, then the mass is going to be 27.29 grams. Right? Can you see how that goes? If the percent is 27.29 carbon, and if we have 100 grams of it, then there's going to be 27.29 grams. The formula weight is 12.011, and we'll calculate the moles right here, right now. Right here, right now. I'm going to calculate the moles if there are 27.29 grams divided by 12.011 grams per mole is 2.272. 2.272 moles, right? Okay, and let's do the oxygen now. Oxygen 72.71%, and if it's 100 grams, it's going to be 72.71 grams of oxygen, right? This is 16.00 grams. Grams per mole, right? So 72.71 divided by 16. Did I get that right? 72.71. That's right. It's going to be a heartache if I misprint something here. 4.544, and so on. Okay? Now, I divide everything by the lowest number. Okay? I'm going to call that n prime, just because I'm making up a new column here. Looks like the lowest number is 2.72. Like I say, 2.272. That divided by 2.272 is just going to be 1. This divided by 2.272 is going to be, I don't know. 2.272 equals 2.000. Aha. I can see that this ratio now is going to be C1O2. Or we don't write it like that, right? We write it like CO2. So it looks like this is carbon dioxide that we're dealing with here, okay? All right, so the final thing I'm going to say in this conversation is that we can get molecular formulas by taking the empirical formula and shifting it, right? So watch this. A compound's molecular formula can be determined from its empirical formula and its molar mass. So if I take my molar mass of the compound and we divide by the empirical formula, it's going to tell us how many times to multiply all those numbers in it, right? This will make more sense in just a second. So let's look at this. Suppose that we know that we've got some compound, its empirical formula is this, and its molar mass is this, right? So if its empirical formula is that, then I take that, watch this, that times 12, 1 times 12, plus 2 times hydrogen is only 1 gram per mole, right? Plus, and there's 1 oxygen there, and that's 16 grams per mole. This is going to be 14 plus 16 is 30 grams per mole, or AMU, right? So if I've got 30 AMU, and I know that the molecule is 180 AMU, then aha, that's going to be 6. So that means that I'm going to multiply all of these guys by 6. So it's C6H12O6, and boom, that's probably glucose. All right, so this is a little bit of a fast introduction, but obviously you can rewind or rewatch any of these examples, and we have more examples coming in class. So hopefully this is helpful.